Now, for single head attention, we're done and ready to move out of the attention layer. But it's time we peel the onion on multi head attention, compare it to the results of our single head attention, and explain the performance benefits. We will keep our single head attention results off to the side for comparison reasons later. Now, multi head attention gives the model the space to learn the relationships between embedding dimensions, group them together in a head, calculate the attention for those dimensions separate from any other dimensions that could produce unnecessary noise, and then concatenate the heads back together and reorder, for lack of a better word, the dimensions back into their original position. Let's understand this deeper though. How do we do this? Well, it all goes back to how the model's trained. We won't dive into how a model is trained too deep or explain much of the terminology. We'll only view it from a 30,000 foot view so we can understand what we need to in order to grasp multi-head attention. For our hypothetical single-head attention, the backpropagation of our error after each batch of training examples updates all of our weights, as if they are one monolithic block of tunable parameters, which in single-head attention they are. The downstream effect of this is that when our query and key matrices are dotted together to assess attention, every dimension is taken into consideration, which naturally causes some unnecessary noise. For example, let's look at our beam query, which had a high need for an action and a high need for an object. Unfortunately, none of our key vectors can satisfy both an object and an action. Our me key has an information about the object but not the action, and our beam key has information about the action but not the object. This frankly results in our model diluting both respective real correlations. Beam's key vector gets dragged down to 64% because the fact that beam doesn't have yet any information on its object was for some reason taken into consideration. And on the flip side, me's key correlation was also dragged down to a mere 19% because it didn't have any information related to an action. All of this added noise is to the detriment of every scalar in the attention matrix. And while it does enable some attention across tokens, we will only ever be able to present a slightly blurry metaphorical picture. Rather than a holistic, one-size-fits-all attention relationship between queries and keys, what we really want is the ability to have multiple attention values reflecting the relationship at more specific subgenres of the entire embedding space. This is precisely what multi-head attention provides. The number of heads times the number of dimensions per head will always be equal to the total number of dimensions in the token embedding representation, meaning the model can keep its same general size of its weight matrices. For our example, we will assume we have 2 heads, each with a shape of 8 rows and 4 columns. When our multi-head attention is trained, our backpropagation of our error only takes into account each respective head's parameters when updating their respective weights, thus presenting the space for the model to learn specific relationships or subcategories of our dimensionality. I want to state clearly that what I am about to showcase is an oversimplification, still because of our binary numbers and still because we only have 8 dimensions. But I think this is the best way to initially approach multi-head attention and will result in you firmly understanding its value and how it can extrapolate out to 12,000 dimensions, like what is in the original GPT-3. Recall that when we did single-head attention, our input to our weight queries was reflective of our dimensions in the order displayed on the screen, and our output maintained that order. But why did it maintain that order? Each respective dot product took into account each respective embedding dimension, so there was surely the opportunity for any of our embedding dimensions to have an effect on any of the resulting scalar values. So why did index 0 refer to our action as it came in and our action as it came out, just contextualized? Well, the simple answer is, since on our way out of the attention layer, our original dimensions needed to be in their proper place, and since there was no part in our architecture that encouraged the indices to change representation, The natural evolution of our one holistic monolith of weight parameters found the smoothest gradient descent while training to be no alteration of the dimension representation and just contextualize the dimensions where they stand. But apart from that, there's no substantive reason why each indices needs to remain the same for each respective dimension, because since our weight matrix is a square dimension by dimension matrix, our input values are identical in each of our dot products. What's different is the respective weight values. So, looking at our single-headed tension weight query matrix, if we reorder our weight column vectors, assuming our model was bent to train our model as such, our resulting query vectors could, technically speaking, have reordered our dimensions' respective needs. Since each head's weight parameters with multi-headed tension are updated independently, it forces our model to do exactly what we're saying here, to bend its respective weights or to categorize its dimensions into groupings that are most commonly correlated. Now, we will need to put our dimensions back in the appropriate order prior to leaving the attention layer, but just put a pin in that thought because we will get there later. One comment, and I don't mean to sound like a broken record, but if we trained our model with different backpropagation rules, the resulting query vectors wouldn't be simply moving the same resulting scalar values into a different order. The weights, especially when we are talking about over 12,000 floating point numbers for each token, would be substantially different than a hypothetical single-headed tension architecture, which again is not really done in practice anyways. But logically, our model with multi-headed tension would have the space to not only quote reorder unquote our dimensions, but also produce much richer and less noisy needs, keys, and values. For our example, though, we're just going to keep it simple and assume the same scalar output values are simply reordered to group the dimensions in two subcategories of 4 dimensions each. This will let us compare side by side our single-headed tension and still show how, even with the same scalar outputs, multi-headed tension enables better performance. Looking at our dimensions, we can logically categorize these into two groups: verb modifiers and noun modifiers. If something has to do with an action, or if something is in the present, past, or future tense, these are all very much verb related. And if something is in the first person, singular, related to an object, or headed in a direction, it's not a perfect grouping, but these can better be categorized as noun modifiers. I'll carry out the math and please pause as needed. Recognize all the noise we were able to sift through simply by giving our model the space to handle the attention at a subcategory level, as opposed to the holistic representation all at once. In our verb modifier head, our beam key provides 79% of the context, up from 64% with single head attention, and it also shrinks the me key's impact to a mere 10%. With respect to our noun modifier head, the inverse happens, even more dramatically. For our beam query, we now no longer are being substantially diluted by our beam key, able to drop it from the staggering 64% of our attention it was consuming with single head attention down to 19%, since the tense and action are being attended to elsewhere. This provides the space to now allocate 46 and 34% respectively to our me and up keys to better attend to our object and direction needs. When we dot these attentions with their respective value matrices and concatenate the output heads back into a single 3x8 matrix, we now have much more context-rich dimensions, but unfortunately they're all out of order. This is one of the key differences in how multi-head attention is implemented, which was not needed for our original hypothetical single-head attention, because those indices never changed where or what they were representing. To get our dimensions back in their proper order, we will introduce one final weight matrix. This is our weight output matrix. Our weight output matrix is a dimension by dimension matrix, which for us is an 8x8 matrix. Since this is a square matrix, it won't affect our output shape at all. But the result of this matrix.matrix operation is our dimensions or our column vectors are reorganized into the proper order. We can visualize this by assuming our weight output matrix is as follows. Now, if we compare our single headed tension output to our multi headed tension output, both of which represent the deltas or the adjustments that need to be made to our initial input embedding, we can see quite clearly that by simply giving our model the space to subcategorize our dimensions and attend to each category separately, we were dramatically successful at sifting through all the noise and adding valuable context for each dimension without diluting or dimming the payload with a bunch of non-related dimensions in each dot product. Now, let this example help you lift the hood of the attention layer and understand why it's structured in the manner that it is. But do not let this example simplify the attention layer to anything that resembles rigid dimensions or inflexibility. When you train a model, it will learn over weeks or months the optimal weights to transform your initial embedding into something that can predict the next token. But while it sounds like I'm kind of contradicting what I have just oversimplified, it's too rigid to actually assume that each dimension maintains its own specific lane throughout the model and never veers. While each dimension by default starts as some abstract feature of the initial token, as it gets contextualized at each encoder of the model, the contextualized output could be the learned progression of the feature set. So while this example, which we'll continue with for the remainder of our transformer explanation, is very helpful in breaking down the role and purpose of the entire architecture, we shouldn't actually view multi-head attention as simply categorize the dimensions and then reordering them upon exit. It is frustrating, but accurate to say that the best way to describe multi-head attention is from the 30,000 foot view. Each head extracts diverse contextual information, abstract from our knowledge, passes this contextual information down through its model, and leverages the weight output layer as a fusion layer, which provides the opportunity for the model to mix up all the hypothetical ingredients that it has pulled from the various heads back into what it learned through training would be the best embedding representation. To say that we don't understand what the attention layer knows is not to say that we don't know how or why it works. At risk of personifying something that is simply just sequential math operations, we give the model enough heads and weight parameters to reach its own conclusions and learn for itself. Now, that was a lot of information, but congratulations, we are officially past the attention layer and ready to move on to our add norm layer.